Hello, welcome to Hangout Cosmo. Today we're talking about gravitational waves. Exciting news in the scientific community. A few months ago, scientists from the BICEP2 collaboration reported detecting primordial gravitational waves for the first time. This set a lot of excitement in the community in science. But another team of scientists, 6 months later, reported that what they detected was probably something to do with foregrounds, noise, due to coming from our own galaxy, the Milky Way. So to discuss this today, we have two specialists in cosmology and gravitational waves. Joining us live from CERN is Dr. Diego Blas. Hello, Diego.
Hello, Anais. I'm Diego Blas from the Theory Division of CERN in Geneva.
Also joining us from the University of Heidelberg in Germany, gravitational wave specialist and Planck scientist, Dr. Valerio Pettorino. Hi, Valeria.
Hi, everyone. This is Valeria Pettorino, and yes, I'm talking from Heidelberg Institute of Theoretical Physics.
Great. So this is very exciting to have you both online because we have a lot of questions about gravitational waves. Let's start from the beginning. What are gravitational waves, Diego?
Well, gravitational waves, a way to understand them is with an analogy with what waves are in general. So the idea is that when you throw a stone over the water and you generate a wave through it, well, it's something that everyone understands. The thing is that the same phenomenon happens when some massive object moves in his trajectory, let's say, and while it moves and it kind of fluctuates, it also generates these ripples, these kind of waves that go away from it. So this kind of energy, if you want, is what we understand as gravitational waves, and it is waves from this side, and also it's gravitational because instead of water, what is really, let's say, being emitted is related to the gravitational field of this object.
So you're talking about ripples, and you're making this analogy with ripples in a body of water, but where are the ripples physically? What's being, what is the thing that's propagating?
Yeah, one of the basic ideas of theoretical physics nowadays is that all the interactions are described by fields. So in the same way that there is, in this analogy, there is water filling the space close to the stone, also in the universe there are fields, okay, that populate the universe, and they can be excited by different phenomena. Okay, in this case is the gravitational field. You want the gravitational ether. I don't want to use the word ether, but it's a kind of really, let's say, medium, if you want, that is really modified by the presence, and by not only by the presence, but by the movement of masses.
Okay, so do we expect gravitational waves everywhere in the universe then? Because
Yes.
you said it's related to massive objects. I guess there's massive objects everywhere in the universe.
It's similar to light in the sense that, well, around us we are always surrounded by light, for instance, and we are also surrounded by other waves that we cannot see because they are so difficult to detect, in a sense, right? So they go through us, but they are all over the place. Yeah, in this sense, gravitational waves are very abundant, but very difficult to see.
So just a reminder that you can ask questions to Dr. Diego Blas from CERN and Dr. Valeria Pettorino from the University of Heidelberg. You can ask them via Twitter using the hashtag HangoutCosmo. We already have a question coming in. So you talked about the propagation of gravitational waves. One of the questions asked on Facebook is, at what speed do gravitational waves propagate? Diego.
Yeah, in the theory of general relativity, which is the theory we use to describe this phenomenon, the speed of propagation is the speed of light at vacuum. That was very important for Einstein when he developed this theory. Precisely, he wanted a theory of gravity where this was true, and he spent so many years, and he finally found it.
Valeria, do you have any other comments on that?
Not only that, of course, if the theory of gravity is modified with respect to general relativity, then you can even expect to see changes in the speed of gravitational waves. So actually, this can be a test for modified gravity theories.
So are scientists looking to detect gravitational waves specifically to test gravity? Are there other things that we can learn from gravitational waves? Diego.
There are so many things we can learn from gravitational waves because in the end it's like being blind and suddenly starting to see, because as I said, it's a sign. It's really a signal that is really arriving from many places in the universe, from many phenomena, that you are not able to see now. Okay, so once you start detecting them, you will be able to access, let's say, places that nowadays are impossible to access. Like, for instance, I can make an analogy with the sun. Okay, the sun, we only see the surface of the sun by light, but there are some signals created at the center of the sun that directly go through. They are so weakly interacting with the sun itself that they really go through it and arrive to us. These signals are arriving to us in the form of neutrinos, which is a different kind of signal. So for gravity waves, the idea is the following: that as soon as we start detecting them, we may be able to access places where now we have no clue what's going on, right? So it's going to be a full revolution.
So I really liked what you said, that it's like being blind and all of a sudden you're able to see.
It's exactly like this.
What, I mean, has this happened already? Have we detected gravitational waves? It was the first time with the BICEP 2 team in March?
No, not really. Well, yes and no in a sense. But first, that is not clear whether they detect gravitational waves, as we will discuss later. But before, what was detected was the effect of the gravitational wave on the system emitting them. And coming back to this analogy of the stone suddenly falling into
in a body of water.
Ocean, yeah, let's say. Imagine that you see the stone falling, and suddenly it starts to move slower.
Mm-hmm.
Okay, then the first thing but you are not able to see the water because it's transparent. Okay, the first thing that you can think of is that, oh, maybe what happened is that there is something that stopped this movement. Okay, that created some energy, and once you start being more precise about your measurement, you can start seeing these water ripples. So here is the same. There are some systems in the universe called binary pulsars that emit a lot of gravitational waves, and you see that the effect that we expect from this, which is that the orbits of these systems are modified. These effects are actually being seen. So everyone, and there was even a Nobel Prize for it.
So when was this first detected with binary systems?
In the late 70s. I don't know exactly the date.
Okay,
the Nobel Prize was in '93.
So gravitational waves were something that was predicted by Einstein's theory of general relativity,
yeah. Yes.
Detected for the first time with binary pulsars in the 70s. There was a Nobel Prize for this. But then what happened 6 months ago? What was the big announcement? Valeria, can you tell us what was the BICEP 2 team looking for?
So they were observing the cosmic microwave background, and in particular this radiation that emits in the microwave, which is basically light that started to travel about 13 billion years ago. So it really gives us a snapshot of the universe as it was really young.
And so actually I see you have a picture of the cosmic microwave background behind you. Can you show it to us?
Yes, this is a map of the temperature differences that we see in this radiation when we look in different directions in the sky. So this radiation is characterized by intensity, so temperature, and again we are interested in tiny differences in temperature when we look in different directions, and also by polarization.
So can you tell us what is polarization? That's not what you have on the map behind you.
No, this is a map of the temperature that was published by the Planck collaboration, which is a satellite basically that observed the temperature and also polarization, but for the moment it delivered the map for temperature. Instead, the BICEP team focused really on polarization, and polarization is related to the orientation of the oscillations of the light that comes to us, of this cosmic microwave background.
So it's some kind of extra, something that's extra that's encoded in the temperature that we're measuring from the BICEP.
It's complementary to the information of the temperature, and it gives us information on the orientation. So it's a directional information, not just a number like temperature.
And BICEP, it's also a space telescope?
No, BICEP is a telescope on ground. It is at the South Pole. And so, in fact, while Planck from space can provide maps like that, so at all scales, in full sky, BICEP looks at a smaller patch in the sky, because again, it's from ground, but at the same time with a higher resolution.
So what was BICEP2's discovery that they announced in March?
So there are two types of polarizations, E modes and B modes. And the thing is that gravitational waves are basically the only kind of ripples, say, in space-time that can produce this particular B mode polarization. This classification is just due to different orientation patterns.
So they're not actually directly seeing gravitational waves, but they're seeing some effect in another measurement that theoretically could only be caused by gravitational waves.
Exactly. So they were looking at the polarization of the CMB, of the cosmic microwave background, and in particular at B modes. And they saw a signal that was really what they were expecting to see for, say, due to gravitational waves at the scales, at the right scales, where you would expect an imprint left on the B modes by gravitational waves.
Great. So what I understand is the major announcement that the BICEP2 team made in March was that they detected primordial gravity waves, right? So we already detected gravity waves with binary pulsars. So Diego, what's important about the primordial side of this?
Well, it is really important. There are different sources of gravitational waves which are around us. And then there are also primordial gravitational waves. And the amazing thing about primordial gravity waves is that they are produced in a very early stage in the universe evolution. In particular, a stage that we cannot access through light, for instance. It's very similar to this analogy I made with the sun. Mm-hmm. So when you look at very far away objects through light, at some point you hit a wall. There is a stage at which you cannot really go farther. It's like a kind of, if you want, a kind of cloud that is in between. However, through gravity waves emitted before this time, let's say, you can have access to all this era of cosmological evolution. Okay.
So and what do you want to learn about that time?
Okay, you can learn many things. You can learn things about the way they were emitted, and you can learn things about whatever happened between the time at which they were emitted and today.
And there was talk about inflation, that these primordial gravity waves are important for inflation. What's that?
That's the other side of the. I was before being a bit more general, but also there is another very good aspect of primordial gravity waves coming from inflation. So there is like this distinction that could be primordial but not from inflation, and primordial are from inflation. So the idea is that inflation is cosmological inflation is the best.
Quickly explain to us what's the key about inflation.
About inflation in Argentina or in the cosmos?
Cosmos.
So in the cosmos, the idea is that there is a very good theory of how the structure in the universe, so when I talk about structure, I talk about matter really, was created by a process which is, let's say, very simple, okay, and that we kind of understand. And the idea is that it's called inflation because it's based on the idea that very early in the history of the universe there was a period of exponential expansion, like inflationary expansion, of a small region of space-time, and from this we were kind of generated. And the idea is that if we are generated, in the sense that the matter around that is generated from this very small region, also gravitational waves are generated.
Okay, so primordial gravitational waves were crucial for understanding a very key moment in the history of the universe that's theoretically very important because it explains a lot of things that we see today. And so that was the claim from the BICEP2 team, that they were detecting something related to inflation. Now, recently, the Planck team released a paper saying that it was probably something else that they could have taken into account. Valeria, could you explain to us what the Planck team said?
Yes, the fact is that there are tiny grains, say, in the Milky Way, such that, say, oriented with respect to the magnetic field of the Milky Way, in such a way that they also generate, when heated up by starlight, the same kind of signal that can be generated by primordial gravitational wave.
Okay, so we're detecting one signal that can either be something primordial from the very early universe, very, very far away, or right in front of us in the Milky Way. And so it's kind of mixed up.
We're detecting polarization, but this polarization signal could be either generated by a local phenomenon, so something related to our Milky Way, our galaxy, or which is somehow for us, let's say, a bit less interesting, because we were hoping to detect instead the signal of primordial gravitational waves, primordial B modes.
So today, can we say for sure we haven't detected primordial gravitational waves yet?
No, we cannot say it for sure. So at the moment, again, BICEP had at the beginning didn't have information about how big the signal in these tiny grains was, in this dust, and attributed the whole signal to gravitational waves. On the other hand, Planck delivered a first map of the polarization due to dust, so to these tiny grains in the Milky Way. And it turned out that it was much bigger than expected. At the moment, however, we don't know yet if there is nothing left due to primordial signals, so due to gravitational waves.
So Diego, what's next theory, in the theory side of this?
Well, in the theory side, well, there are about primordial gravitational waves and about astrophysical gravitational waves. I think there is a difference.
So primordial gravitational waves, what's the next step?
For the theorist point of view, I think the only thing that we can do is wait. In the sense that the parameter space of possible theories predicting gravitational waves has been explored. And now we are really waiting to see what's the answer coming from experiments.
Okay, so the theorists are waiting for the observers, and Valeria, what's the next steps on the observational side?
Well, the Planck collaboration and the BICEP collaboration are working together, and they are collaborating now to share information and data, because BICEP has, again, a higher resolution in that small patch, and Planck has instead information on the dust, let's say, and also information on full sky and different frequencies. So the combination of these analyses will tell us if there's something left. And on the other side, there's going to be also several other experiments on balloons or grounds, and possibly other proposals also for other satellites, which will look with higher resolutions and, most importantly, at different frequencies, in order to try to disentangle, to separate the amount of signal which is due to dust, so to a local Milky Way phenomenon, and other part, if left, of signal, which is instead the interesting primordial part that gives us information about the physics of the early universe.
Okay, great. So the theorists are waiting for more data, and the observationalists are really working on it with more data from space telescopes and ground-based telescopes and balloons. So that's great news. Thank you very much for joining us to talk about gravitational waves. Thank you, Diego Blas from CERN. Thank you, Valeria Pittarino from University of Heidelberg. Feel free to continue to ask questions via Twitter. Valeria and Diego will answer them on Twitter at their leisure. So thank you very much, and see you soon.
Thank you.
Thank you.